In this video, we're going to talk about the general format for linear systems, the general equation that describes linear systems, and specifically we're going to discuss the roles of poles and zeros. So as always, let's start with an example of a first order low pass filter. Now if I want to calculate the transfer function h of s, the Laplace transfer function, it's going to be a voltage divider. The capacitor is going to have an impedance of, instead of 1 over j omega c, it's going to be 1 over sc, and over r plus 1 over sc. And that's a complex fraction, so let's tidy it up a little bit. I can equate that to 1 over src plus 1, and let me just leave it there for now. So one thing that we're going to get in the habit of doing is whenever we have a linear system, we're going to think about the poles. Okay? And the poles are, by definition, any value of s that makes the denominator 0. Makes the denominator of h of s equals 0. And we're also going to talk about zeros, which is the same concept. It's any value of s that makes the numerator equal to 0. So let's start with the zeros. Let's start with the numerator. Are there any values of s that make my numerator equal to 0? And the answer is there are none. Okay, there are no values of s that will make my numerator anything other than 1. So in this case, I can say we have no zeros. Okay. What about poles? Well, that's a little bit different. Let's see. My denominator is src plus 1. And if I set that equal to 0 and solve for s, I find that s equals negative 1 over rc. Okay? And that is, I have one pole, and it's that value. It's negative 1 over rc for whatever values of resistor and capacitor I use in this particular equation. Now, let's compare that to what we talked about in the previous lecture. In the previous lecture, we said that when it comes to the Laplace transform, generally speaking, we can think of it as having a real part plus or minus an imaginary part. We said that the imaginary part determines oscillation, and the real part determines decay or expansion. And in order to have decay, we need to have sigma less than 0. So sigma less than 0 means decay. And every decay has a time constant, and we know that the time constant has to be negative 1 over sigma. Those are all things we talked about in the previous lecture. So let's compare that to what we have here. In our case, we have s equals negative 1 over rc. Well, resistor and capacitor are both real values, so that has to be a real number. So that's my sigma. And then plus or minus j times what has to be 0. Okay, the only way this works is if omega equals 0, because I know that this is plus 0 over here. So let's see what that means. Well, we know that the imaginary part sets oscillation. Okay? And since my imaginary part is 0, that means this system will not oscillate. It has no inherent tendency to oscillate. It will oscillate if you put an oscillating input into it, but the system by itself doesn't have any natural tendency to oscillate. And I'll show you what that means in a minute. Now over here, this is the envelope. Okay, it is negative, which means the system tends to decay. And we know that the time constant has to be, oops, not sigma, the time constant has to be negative 1 over sigma, which in this case is going to be RC. And what's happy about all of this is that this is actually things that we already knew. Okay, we've just found different ways of deriving something that we already knew. So for example, if we look at the impulse response of this system, okay, so the impulse response of a first order low pass filter, which I believe we've looked at more than once, is going to look like this. And what you'll notice is that there is no oscillation. Right? If you just put a piece of energy into the system and wait to see what happens, it does not have any sort of, actually that's not what it would look like. It does not do anything like that. It doesn't oscillate. Okay, there is no oscillation. It just goes down exponentially. And why is that? That's because the pole is purely real. The pole doesn't have any imaginary component to it. What it does have is a time constant that's equal to 1 over RC. And here you go, there's that time constant. So you know the time it takes to decay all the way to 0 is about 5 time constants, about 5 RC, which is what we already knew. Now, all of this is for a system with one pole and no zeros. So the question is, what happened if you have a more sophisticated system? And we're going to close out this video just by writing down what a more complicated generic system would look like, and then in the following video we'll talk about how to interpret it. So the generic system is going to look like this. So the generic linear system is defined as follows. H of S equals, now we are going to have in the numerator, we're going to have S minus 0, 1, S minus 0, 2, and in fact you could have as many of those terms as you want, all the way up to S equals, S minus 0 sub, I don't know, let's say we have n zeros. And in the denominator, you would put your poles. S minus pole 1, S minus pole 2, dot, 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 times S minus however many poles you have. All right, and you know this works because if you look at the denominator, let's look at this term. If S minus P1 equals 0, then my whole denominator goes to 0, which is the very definition of a pole. And that happens when S equals to P1. Okay, so when S is equal to the value of the pole, my denominator goes to 0. Okay, and that's all I was trying to achieve by writing it like this. And finally, for completeness sake, this can all be multiplied by a scalar constant, g, because that doesn't affect the locations of any of the poles or the zeros. So that's the generic form. Okay, and some systems can be very complicated. They can have dozens of poles and dozens of zeros, and depending on where you locate the poles and the zeros, you can get your system to have different kinds of properties. And we're going to spend the next few lectures talking about what those properties are and how they relate to the poles and zeros. And in the very next lecture, we're going to talk about how you can use this generic format to do some very quick calculations on your system properties.